Okay, so that's perfect. So regarding the issue on Eve not being able to see the lecture slides, I think as far as I can remember, Mr. Magando did re-enable that. It was blocked because of the semester test on Saturday. So if all of you can't see them, I'll have to follow up with them. But I will share the slides as usual, so you should be able to follow the lecture. So just do that. Okay, so this. Yeah, so let's go back to Eve. Okay, so let's do this. Okay. Yeah, so basically the whole point of this lecture is to provide a summary of the design patterns. So this lecture is very important for your semester test 3. So just keep that in mind because we will use some of the aspects from this particular lecture to test your understanding of design patterns, right? So very, very important. Keep that in mind. I'm not sure if this has volume control, but it sounds like it's too loud. Okay. So basically, we'll look at the design patterns. We'll look at the golden rules for design patterns. So where do you use which pattern and so forth. We'll look at a comparison of design patterns. So how, for example, can you compare two different patterns? We'll look at something that's called patterns of patterns. Okay, so just to recap on what design patterns are, they're a general reusable solution to a commonly occurring problem within a given context, right, in software design, right? So that's the whole point of design patterns, right? So it's a set of solutions that you can always apply to a problem that always occurs, right, or that occurs commonly. Although they are not a finished design, right? So a design pattern is just a structure, right, or a framework for solving a problem. So it's not the solution to a problem, right? So you can also say that they are merely a skeleton, right, to the actual solution to the problem. And their description or template for how to solve a problem that can be used in many different situations, right? So you can think of a design pattern as a template. This is not the same as a function template or a class template like in C++, but this just means, you know, like a framework, right, that you can apply when building a solution to a problem. So what are the golden rules for design patterns? So clients should always call the abstraction, right, or the interface when interacting with the pattern, but not the exact implementation, right? So what that means is the client of a design pattern should know about the interface, right? So for example, in a visitor design pattern, the client must know about a visitor interface and a visitable interface, right? If it's an abstract factory, they need to know about the whatever interface represents the factory, right, or the class that creates other objects, right, and also the interface for the objects that are being created, right, the products, right. So that's very important to understand. So, and that's the whole point of the abstraction, right? You want the client to not worry about the implementation details, right? They should only care about the interfaces that represent the design pattern. So future changes should not impact the existing system. And this is the most important rule of design pattern. If, for example, I add classes that inherit or implement the interfaces in my design pattern, that should not change the code from the client side, right? I should not have to modify the code in main, for example, if I add certain classes that implement the interfaces in my design pattern. So future changes must not impact the existing system. And then design patterns should have loose coupling. What that means is there should not be a strong dependency between the client code and the classes that are involved in the pattern, right? There should be a very weak dependency, right? So that if I change stuff about the classes in the pattern, I don't have to change much in the client side, right? Actually, preferably, I shouldn't even have to change anything on the client side. Okay, so let's look at design pattern comparison, right? So this is just a series of tables that show, where you can apply a design pattern, what its limitations are, and so forth. So the first one is the visitor design pattern, and it's a behavioral design pattern, and basically it represents an operation to be performed on the elements of an object structure, and you apply it when you have distinct and unrelated operations to perform across a structure of objects. So the aim is to decouple the logical code from the structure of the design pattern. The limitations of this pattern is that arguments and returns must be known, right? So for example, for the visit methods in the visitor design pattern, you have to know all of the visitable objects that are part of the design pattern, right? So you need to know the arguments to your methods, and you need to know the return types of all your methods, right? So that's the only limitation of the visitor design pattern. And a new element results in a new method in every visitor, and that is true, right? So if you think about the visitor code of the visitor design pattern, if I add a new visitable, it means I need to add another visit method inside of the visitor interface, right? So the more visitables I have, the more visit methods I'm going to have, because each visit method is dedicated to each visitable object. The observer design pattern is also behavioral, and it basically defines a one-to-many dependency between objects, right? So we saw that as well. You have one subject and you have many observers, right? So when do you apply this? You apply it when you have an object that needs to share its state with others, right? So we even made an example about a blog, for example, that the subject is the writer of the blog or the blog itself. And when the state of the blog changes, all the observers of the blog are notified and they update their state accordingly. The limitations of this design pattern is that it's difficult to see the path through the code. So like through the different chains of observers, right? So when you analyze the code in the observer design pattern, you have a way you have to notify the observers, and then the observers have to update themselves, and then they have to update their states and all of that stuff. And for each observer, that might be different, right? So it's difficult to see like the exact flow of control between the subject and all the observers, right? So that's the limitation of this pattern. Another limitation is that the subject holds a reference to an object until it is deregistered, right? That is true. In the observer design pattern, remember, in the subject, you have a list of observers, right? So, which means that you have a reference to all of those objects until you deregister them, right? So that can cause memory leaks. And it also depends on the language that you're using, right? If you use the language like C++, where you have to manually deallocate stuff and delete pointers and all of that, when you detach objects from when you detach observers, from the subject, you have to remember to deallocate all of the memory, right? If you don't deallocate those pointers, it can result in a memory leak, right? So in Java, for example, you have a garbage collector, so that reduces the chances of running into things like that. And then you have the command design pattern, which is also behavioral. And if you remember this design pattern, it's basically encapsulating a request into an object, right? So you can create a command class for turning on a light, for example. You can create another class for turning off a light, right? The main thing is that the request is turning the light on or turning it off, right? So you take that and you make it an object, right? So that's the logic behind the command design pattern, right? You create an object for each command, basically. And you basically apply it when you want to keep track of a history of requests, right? So you want to keep track of a log of all the commands that were executed. You can also use it if you want to have callback functionality, where let's say, for example, you issue a command, but you don't want to have to wait to know that it has been executed, right? So similar to callback functions in like languages like JavaScript and all this stuff. But the whole idea is you want to issue commands, but you don't need to wait to know if they were executed. You can continue and do other stuff. Also, you can use it when requests need to be handled at like different times or in different order, or if an invoker needs to be decoupled from the receiver of a command, right? So in this case, you want to have a particular class that invokes commands, but it doesn't really know how the receiver of the command executes the command, right? So you want to decouple those two so that the receiver doesn't have a strong dependency on the invoker, or the invoker doesn't have a strong dependency on the receiver. Again, limitations. This pattern forces a lot of command classes. That actually makes sense. For every command, you will need to have a class, right? So it's similar to the visitor design pattern in the sense that for every visitable, you need to have a method in the visitor interface, right? So scalability problems. So it can make your design cluttered. Another limitation of the command design pattern is that it obfuscates command behavior choice and causes maintenance issues, right? Especially for a central controller or an invoker. The reason for that is you know that these classes are performing certain commands, but you don't know how they are performing those commands, and you don't have access to their code, which means that if one of the classes suddenly malfunctions, or like the code is causing memory leaks or errors or logical errors for certain situations, it's hard to debug that code because your central controller does not have access to it, right? So that's a limitation of the pattern. And then structural design patterns, we have the adaptive design pattern, which basically converts the interface of the class into another interface that the client expects. We even did an example of this, where we had a class that wants an array of integers to be sorted, and we had a sorter class that could only sort array lists, right? So then we created an adapter class, which takes the array from the client, gives it to the, like converts it to an array list first, gives it to the sorter. Once the sorter sorts the array list, it converts it back to an array, and then gives the array to the client, right? So that's the whole idea of the adaptive pattern. Where to apply, very simple, when you have a class, but it doesn't meet the requirements of the interface that you are looking for, right? So limitations of this design pattern, sometimes it can be seen as a fix to badly designed code or a badly designed system. So it's kind of like putting a bandage on the problem, but not really solving the problem, right? The issue is you have a sorter that sorts array lists, but you're not fixing that. Instead, you're just creating an intermediate class that will, convert, do the conversions, and then give the data back to the client. So the problem with that is that it also adds complexity to your code, because you're creating extra code to make this thing work instead of just fixing the existing code and get that to work. So that's the limitation of the design pattern. Also, debugging is difficult because you have the adapter class that doesn't really do the job. The job is done by another class that is hidden from the client, right? So it makes debugging more difficult. Okay, and then proxy design pattern, another structural design pattern. This basically provides a placeholder for another object and then controls access to it. So we did an example with the a class that holds a secret, and then the proxy only gives the secret to the client if the client has the correct credentials. Right? You apply it when the object being represented is external to the system, or objects need to be created on demand, or access control for the original objects is required, or added functionality is required on access, right? So basically, most of the use cases for this design pattern is if you want to have access control, right? Or you want to add like additional functionality before performing a task, right? So you create this proxy class and it does that for you. Limitations, magic could be happening that the extender is unaware of, right? So it's like the adaptive design pattern, right? The proxy knows that, you know, like the class that is being hidden is doing a certain job, but it doesn't really know how it's doing it, right? So it goes back to the idea of like debugging issues, right? So that's the limitation of the proxy design pattern and the adaptive design pattern. Also, you can't do self-calls. So that happens like in a situation where, let's say, like in the proxy pattern, like because so the pattern itself, like the proxy class itself, it delegates work to another class, right? So the class itself, so you can't, for example, make calls like to certain attributes that belong to the class that is being hidden away from the user, because those attributes don't belong to the proxy class, but they belong to the class that is hidden, right? So it kind of limits the functionality that you can have inside of the proxy class, right? Because it doesn't have the private member attributes of the other class or the state of the other class. There's identity issues, that is definitely true, especially when comparing references, right? Because the proxy is not the real object, right? So there'll always be that obfuscation or that abstraction. The smart design pattern, structural design pattern as well, we said it produces a unified high-level view as an interface of a set of subsystems, right? So remember, we made an example about the flight, I think it was a travel agent class that knew about cars and flights and hotels, and then the client simply knew about the travel agent. And when they made a request to the travel agent made the request to the different subsystems, right? So the travel agent is the facade, and the client only knows about it, but it doesn't know about the other subsystems, right? So where do you apply it if you want to simplify an interface, right? And you also apply it if you want to provide exposure to the caller, but hide the underlying packages from the caller, right? So it means you're exposing the caller to certain functionality, but you are hiding, you know, like the way in which that functionality is achieved, right? The limitations of this design pattern, subsystems are hardwired into the facade, right? And that is true. So the facade knows directly about all of these other subsystems, like the car class, the hotel class, and the trip class, right? So that creates a dependency between the facade and all of these subsystems. And in order to support underlying change, the facade needs to be made aware of it. Goes back to the dependency. If you want to change the car class, you need to update the facade as well because it knows directly about the car class. If you want to change the fly class, you need to make changes to the facade as well because it must know directly about the flight class or the hotel class and so forth, right? So there's a strong coupling between the facade and the subsystems. And then we also looked at, so this is the structural design patterns. And then we looked at the creational design patterns. There were only two of them. There was the abstract factory and the object pool, right? So the abstract factory basically provides an interface for creating families of related or dependent objects without specifying their concrete classes, right? We made an example of a vehicle, right? So you have a factory that produces vehicles. The client knows about vehicles, and they know that vehicles can do something, right? We had a method called inspect, where all vehicles can be inspected, right? So you just call the inspect method, right? But if you wanted the functionality that is specific to a vehicle, then you had to perform a cast where you cast the vehicle product into a car, for example, so that you could call the methods that belong to the car, right? So abstract factory basically produces products without specifying their concrete classes. You apply it when you want to decouple the concrete class from the client, right? So the client doesn't need to know about the car, it just needs to know about the vehicle product because it cares about vehicle products and doesn't really care if it's a car or a truck and so forth. The limitations, if new attributes are added to the abstract product or the abstract factory, it results in the change in the interface, and that is true, right? If you add something to the abstract product, then like obviously like you need to make changes in such a way that the clients will you know, like know about those extra methods. Or if you make a change to the abstract factory, then you might have to make a change in the abstract products as well, or the concrete factory, and so forth. Not a great limitation, but extra work nonetheless. Another limitation is that the type of factory needs to be determined at runtime, right? So, okay, so also not a great limitation, but like what this basically means is that, so if for example you create a factory, like you need to determine that only when the like not at compile time, but when the system is already running, right? So like which factory you want to create. Yeah, but also depends on the application. So yeah, okay. So object pool, also a creational design pattern, uses a set of initialized objects that are kept ready to use in a pool, right? So we saw an example of this when we were creating reusable objects, right? So the clients can create the reusable objects and place them in the pool, but only one instance of the pool can exist at a time. So you can't have many instances, and in order to enforce that, we had a private constructor to make sure that you couldn't instantiate the pool, but rather you had to call a function called getInstance that would create an instance of the pool and return it to the client, right? And then we could add stuff to the pool, or we could remove stuff from the pool. Yeah. So we use this if we want to improve performance significantly when the cost of initializing an object is high. Oh yeah, also when the cost of initializing the object is high, so they would rather keep it in a pool so we don't have to initialize it again. When the rate of instantiation and destruction of objects is high, right? So if we have an application where we have to keep instantiating stuff or destroying stuff. Complicates object lifetime, that's one limitation, because it means that objects no longer depend on the scope in which they exist, right? Because instead of them being de-allocated by the garbage collector, you basically place them in a pool, so that you know, if you want to use them later, then you use them, right? So obviously that kind of complicates how long, you know, you want the objects to exist for and things like that. Requires continuous resources, because even though you are not creating and destroying, there are objects that you are keeping there. And as long as there's an object, it means that that memory location will always be dedicated to the object, right? So you need continuous resources. Obviously, when you put the objects to the pool, you might want to reset them to their default state as well, right? So that's another limitation. Not really a limitation, it's just that, you know, it's extra work that you have to do. So every time you're done using an object, you have to reset it before you put it back to the pool. Also requires thread synchronization if an object is mutable, right? So what that means is when you do multi-threading, that will make more sense. But it means that if you have separate threads that are running and that object is in multiple threads, if those threads, for example, like there's a problem with, like there's something called a racing condition, so this won't make sense now, but when we do multi-threading, it will make sense. An object could be changed in one thread, whereas another thread still wants to use it, but it wants to use the previous state of the object before it was changed, and that creates a problem. Yeah, so let's just quickly finish this. So when choosing design patterns, you always need to choose the best pattern for the job, right? So this may result in using multiple patterns to complete the job, right? It also could result in something that is called patterns of patterns. So you have a pattern, a design pattern that kind of contains another design pattern, like as a substructure or sub-pattern, right? Depending on the complexity of the task. So inappropriate use of patterns may unnecessarily increase the complexity of the system that you are creating, right? So more is not always better, right? So just because you're using a lot of design patterns doesn't mean that your system is more efficient, right? So you need to be careful how you choose your patterns. So yeah, so we managed to finish this. We started the class 20 minutes later. I actually had planned an example of the visitor design pattern to do with you guys, but I'll have to figure out how I'll get it to you. But yeah, sorry about that. It was a class that went over time, or rather a test that went over time. I did report to the HOD, but yeah, there's literally nothing you can do about it now. So yeah, thank you for your time, and I will see you guys tomorrow in the practical session. Thank you. Yes.